Homogeneous linear differential equation. Differential equations that with constant coefficient. Okay, constant coefficient. So this method that we're going to discuss can be applied only if the coefficient is going to be constant. Okay, we stay with the second order, but we extend it for you quickly. Okay, anything to do with the second, a little bit of algebra, you need to get it. Now, what is going to be the idea? So let's consider about this equation. Okay, consider following. Okay, the second order equation, differential equation of this form. You see, coefficients are constant. There is no px, qx, nothing. It's going to be numbers. A y double prime, that's b y prime, that's cy equal to this. Okay, of course, these are numbers where A, B, and C are numbers. So this is a differential equation with a constant coefficient. We did this one right at the beginning of the course. Remember, we give you a function y equal to the e to the rx, and we ask you to find the r so that y equal to the e to the rx is the solution of the equation. We do the same thing over here. Okay, we assume that the solution is, okay, assume that y equal to e to the rx is the solution of the equation. Is a solution. We force the solution to be of this form, okay, of the equation. Of the equation, of course, when r is a number. When r is a number. Okay, so if you assume that this is the solution of the equation, it must satisfy the equation. So get the derivative of the function. So y is e to the rx. You differentiate it. You know, exponential function never change. You need to do your prime, which is r e to the rx. And you differentiate it again, y double prime. So you get another r, so that you r is squared e to the rx. Okay? So drop this function into your equation. So if you drop it into the equation, what is going to be the result? It's going to be a times y double prime, which is r squared e to the rx, plus b times y prime r e to the rx, okay, plus c times e to the rx equal to the 0. Because you suppose it's a solution. You know that the exponential function never change, never 0. So drop by e to the rx. If you drop, what's going to be the leftover? The leftover is going to be, you know, this is y because e to the rx is never 0. Okay, so you arrive at this equation. AR squared plus b times r plus c equal to 0. Look at this equation. Call it a star. Okay, this equation will tell you something. It will tell you that e to the y equal to the e to the rx is the solution of your differential equation if and only if r is the zeros of this quadratic equation. So this means in order to solve the differential equation, you need only to solve this quadratic equation. And you know that if you want to solve quadratic equation, there are 3 possibilities. You may get 2 real solutions. You may get a repeated solution, or you may get complex solutions. So we have to consider all of them. We come back and we prove that the solution that you get from here, they are all independent. The Wronskian. We prove that the Wronskian is not equal to 0, so automatically you can solve all these type of differential equation nicely. Okay, so we have to a couple of expressions that we explain. This star equation, we call it characteristic equations. Okay, same expression that we use in linear algebra, using discrete mathematics. And we are going to use this one again when we get to the system of the equation at the end of the course. Okay, star is called the characteristic equation. Okay, characteristic equation correspond or of the differential equation. Of the differential equation. Differential equation. And it's very easy to write. You see, it's like y double prime AR squared plus BR plus C equal to 0. Then, therefore, this is it. As I talk about it, that y equal to the e to the rx is a solution of differential equation. Okay, of differential equation if and only if. Okay, if and only if r is a 0 or is a root. Okay, 0 or a root of that quadratic equation. Okay, of the star equation or characteristic equation. Of the characteristic equation. Characteristic equation star. Any question? Now there are 3 possibilities. We're going to check each possibility and propose the solutions. Okay, there are 3 possibilities for that equation. So what's going to be the possibilities? The first one, we have 2 distinct solutions, 2 real solutions, okay? We call it distinct real solution. This idea are going to be extended to the higher order, just using those expressions again, distinct real solutions, real roots or solution. We refer to the roots and the zeros, that characteristic equations. Here we are, if R1, okay, if R1 which is not equal to the R2, R2 solutions are zeros of the characteristic equation. Then Y1 equal to the e to the R1x and Y2 equal to e to the R2x. Okay, these are going to be solution of the differential equations. Are solutions are going to be solutions of the differential equation such that can easily prove that, because they are all exponential functions, we can easily prove that the Wronskian of y1 comma y2 is never 0. Because, you know, when you differentiate, everything will be exponential function. So at the end, you get something like e to the r1 minus r2x, which is not going to be 0, okay? So we have 2 solutions. Wronskian is not equal to the 0, so the linear combination of these are going to be the general solution of a differential equation. Okay, so y equal to C1 e to the r1x plus C2 e to the r2x is going to be general solution of a differential equation. Okay, is the general. Okay, it's going to be the general solution of that differential equation. Solution of the differential equation that is done. Easy and nicely, can be done. So that's the case one, when you have two different ones. Again, in discrete mathematics, the solution we consider as this is exponential function. Then over there, we consider the solution as a form of sequence, r to the n. So if r is equal to 2 to the n, it's going to be, a solution of your correspondence. And we do exactly the same thing. Okay, that's case one. Any question? Case two, when we get the repeated solution. Okay. If r is going to be repeated, one of the solutions is e to the rx. You know it. We're going to find the second one. Use the method of the reduction of the order that we talked about it just today. You find out the second solution is going to be x e to the rx. And then you have the situation, okay? That's why we talk about that method first, okay? So the second case, repeated the real solution. Okay, that's going to be case two. If a solution is repeated, okay, that's it, repeated, real solution. I say solution because this can be used for the higher order. Okay, there you are. In this case, if they are the same, if R1 equal to the R2 equal to the R is a repeated solution. Repeated real solution. Okay, then Y1 equal to the e to the Rx is going to be a solution of differential equation, okay? Is a solution. Okay, a solution of your differential equation. Okay. And we can use the method that I talk about it, and it can be, okay, it can be shown if you like, or proved by the method that we talk about it, by the reduction of order, which is the one that we talk about it today. By the reduction of the order method, we can prove that, okay, Y2 equal to the X times e to the Rx is also a solution of a differential equation. Is also a solution of a differential unit of the differential equation. So in this case, the general solution, Y1 equal to C1 e to the Rx plus C2x e to the Rx is going to be the general solution of your equation. So one of the solution is e to the Rx, you know that. For the second one, we use the reduction of order formula, we arrive at the x e to the Rx. Okay, so this is the general solution. Okay, the general solution of the differential equation. You say in this type of problems, it's the order is 2, so you have only 2 solutions. If the order is going to be higher, you may have more solutions. So in that case, the repetition or the multiplicity of R may be higher. You see, if it's just now repeated once, you get it. If you repeat it twice, then one of the solution is e to the Rx, the second one is x e to the Rx, then the third one is x squared e to the Rx. So we can multiply by x and just go on, get these numbers. Okay, so that's it, case 2. Any question? Now the popular case for application problem in science, of course, the third one, complex solutions. Okay, so in the application problems that you may have in your fields, are mostly complex solutions. Okay, a complex solution or complex roots. That is the type of the equation. Now this is quadratic equation. So the complex solution that you can have is something like what? Something like, if you have alpha plus beta I, the other one is conjugate. It's a positive negative. So you have, for example, 2 positive negative 5i. So the solutions are going to be conjugate of each other. Okay, so if in this case you have 2 solutions, but they are complex. If R1 equal to the alpha, these are a standard notation that we use, so you have to follow these. If alpha plus beta I, this is one solution. The other one is going to be the conjugate, alpha minus beta I. If they are going to be our 2 solutions, are 2 complex roots. Okay, complex roots of that characteristic equation that you have. Okay, it's the same thing. You can form the e to the Rx. But since it's a complex number, you have to show off your knowledge a little bit, simplify it for us. I simplify it for you, then you can write that simplified form. Okay, let's see if you remember something from pre-calculus. Okay, note that. Let's simplify one of them. Let's consider e to the R1x. Okay, I just remind you this from pre-calculus or algebra. If you have e to the alpha plus beta I in there, okay, you can break it into the e to the alpha times e to the I times b. E to the I times b, you can use the Euler formula right down in terms of the cosine and the sine. Remember, this is going to be e to the alpha. Euler formula. You can read this one as the cosine of the beta. That's I times sine of the beta. See, that's going to be the case. Okay, now if you have, now let's see, our solution would be of the form what? We have e to the Rx. Let's simplify this one. E to the Rx would be e to the what? E to the alpha plus beta I times x. So in this case, you multiply it, okay, you multiply together, so that will be e to the alpha x plus, this is going to be alpha x, beta x I. So do it, I did it for the other one, break it. That gives you e to the alpha x, okay, times e to the beta xi. Use the Euler formula, so that gives you e to the alpha x times what? Cosine of the beta x plus I times sine of the beta. See, that's going to be the situation we're going to have. Now, if you, because you repeat this one twice, you see in this case, that y1 and y2, because if you do it for the alpha minus beta I, everything would be the same. Except, you see, except this would be negative beta x. You know that the cosine of the negative beta and the cosine of the beta are the same. But the sine of the negative beta would be negative sine of the beta. You are going to have a negative outside here. And then you write it down as a C1 y1 plus C2 y2. That negative sign is not going to be important. So we can declare that if this is going to be the case, okay, so okay, then y1 equal to the e to the alpha x cosine of the beta x. This is one of your solution. And the second one is going to be y2 equal to the e to the alpha x sine of the beta x. These are going to be 2 solutions, okay, are 2 solutions of the differential equation. It easily can be seen that it's one of the problems in your book, that the Wronskian again is not equal to 0. I prove it for the, for the general one. You find the derivative, you multiply them together, you arrive at sine square cosine square 1, eventually it will be exponential. Okay, so therefore, the general solution of your equation is going to be y equal to C1 y1 plus C2 y1. C1 e to the alpha x cosine of the beta x plus C2 e to the alpha x sine of the beta x. Some people, they pull out the e to the alpha x as a factor, but we prefer to write it down in this form. If you pull it as a factor, we don't mind. Okay, so this is going to be what is the general solution. Is the general solution of your differential equation. You see? Nicely done. Very easy method. You can extend this one to any power. This is the second order. You can do it. Yes.
Why isn't it y2 equal to e to the power of alpha x I sine?
The I would be, we have the constant here.
I wasn't just canceling.
Yeah. That's not going to be issue. Okay. So your job is we give you this, we give you one from each. One from each, you form that equation, check the numbers, quickly write the result. Very straightforward. Okay, any question? So let's check to see how we're going to do it. Quick question on this quiz directly from these methods. Okay. For example, ask you to find the general solution. Okay, find the general solution. General solutions of each equation. Okay, solution of each equation. Each equation. First one. First one is y double prime plus y prime minus 6y equal to 0. You see, it's a homogeneous differential equation of a second order with a constant coefficient. So make the characteristic equation right away. Are you ready? Solution. What's the characteristic equation for this one? The r squared plus r minus 6 equal to this. You see, this order of the derivative is like power of the r. So the order, the second, the first is 0. 6r to the 0 is just 6. Solve the equation by factoring. So that give you r, what's that? Plus 3 times r minus 2 equal to 0. You have two solutions. You can call whichever you like, r1, r2, it doesn't matter. Okay, so the solutions are going to be, I'm going to call r1 equal to the negative 3 is one of them. And the R2 equal to the 2 is the second one. They are different. Okay, that's it. If you like the corresponding solutions, y1 is e to the negative 3x. y2 is, we can do it right away, e to the 2x. So the general solution of the equation, y equal to the c1, e to the negative 3x. That's a C2, e to the 2x, and then you do. I'm not going to do anything else to this equation, unless they ask for the initial condition, if the initial condition would be given to, then you'll be able to find the C1 and the C2. This is the only other option. Otherwise, nothing to do it. Okay, that's the case one. Any question? Distinct solution. Next one is this one, y double prime minus 4y prime plus 4y equal to this. Differential equation with a constant coefficient. So for the characteristic equation, r squared minus 4r plus 4. Factor it. What's the numbers? Minus 2, okay. Minus 2 times r minus 2 equal to r squared. So it's a repeated solution. Okay, so r equal to 2 is a repeated solution. repeated solution. Okay, so the corresponding solutions are going to be y1 equal to the e to the 2x, and y2 equal to the x e to the 2x. Again, you can write the result right away, accepted. So y is c1 e to the 2x plus c2x e to the 2x, and you done. Again, some people like to factor out e to the 2x. You don't have to. It's done. Any question? Number 3. Number 3, y double prime plus y equal to the 0. Differential equation, okay, that's it. Constant equation, second order, constant coefficient. What is characteristic equation for this one? Any suggestion? R squared plus
R.
1.
Oh.
plus 1, okay? So your R squared with y double prime, y prime, R to the okay, 1. Okay, there you are. You know that it cannot be factoried, but it's going to be R squared equal to the -1. Replace the -1 by I squared. So the solution are going to be positive -1. Complex solutions. You pick one of them to identify the alpha and beta. Okay, usually go with the positive one. Doesn't matter which one are you going to work with, okay? So I picked the R equal to the I. So this is like 0. Okay, it's going to be like 0 plus I, 0 plus I. So you call this one alpha plus beta I. So your alpha is equal to the 0, and your beta is equal to 1. Any question? Corresponding solutions. So the y1, remember y1 is equal to what? E to the alpha x cosine of the beta x. So that gives you e to the 0 cosine of x. But e to the 0 is 1. So I1 would be cosine x. So e to the alpha x cosine of beta x, according to the formula. One of them is e to the alpha x cosine of the beta, the other one e to the alpha x sine of the beta. Okay, so the second one, y2 is e to the alpha x sine of the beta x. Again, that gives you e to the 0 sine of x, which is going to be sine x. So the sine x and the cosine x are going to be your particular solutions. So the general solution y equal to the c1 cosine of x plus c2 sine of x. So that gives you the general solution of your differential equation. Any question? So these are going to be, the one that can be done directly. So be aware of the equation. Maybe some equations are not going to be nicely factorable. Any question? So it's very standard equation. Yes.
This is there's only constants, right? So if you don't have any x's in your differential equation, you get to use this. And it's homogeneous.
Where is the constant? What do you mean by constant?
Like in front of the y double prime, the y prime, and the y.
Yeah, it must be constant, only constant. Yeah, you can use this method only with the constant coefficient.
Alright.
When it's not going to be constant, you have to take them separately, one by one. See, we group them, some of them are known, we group them, we can do it. Some other, we can't do these methods. We are going to introduce other methods in future.
Right.
And this can be applied only with the constant. But this cover a large class of application derivative. Okay, now be patient for some of them, like this one. See, 2y double prime plus 2y prime And the good thing is when we get to the out of this chapter, we are going to bring the Laplace transform. Do all of them using the Laplace transform as well in future. Okay, look at this one. Let's see what's so special about this one. Solution. What is the characteristic equation for this one?
4 squared plus 2r plus
2r squared plus 2r plus 3. You see, this equation is not factorable. Use quadratic formula to do it. Okay, so be ready for it. So intentionally, I use quadratic formula. A is 2, B is 2. Okay, C is 3. Go with the quadratic formula, any version you like. Okay, this is it. Negative b plus or minus b squared minus 4ac over 2a. Carefully substitute, simplify it. So negative b would be negative 2 plus or minus inside b squared, 2 squared minus 4ac, 2 times 3. Okay, divide by 2a, 2 times 2. Simplify inside the radical. So that give me negative 2 plus or minus inside. 2 squared would be 4. 4 times 2, 8. 8 times 3, 24. Okay, divide by 4. Go on to simplify it. So that give me negative 2 plus or minus a radical negative 20. Okay, negative 20. So this means the solutions are complex. And we continue to get it. Now that replace the negative sign by I squared and continue. So that gives me negative 2 plus or minus the square root of 20i squared. Okay, 20i squared times 4. I'll simplify further. It's going to be, you have to identify alpha and beta, remember, for the complex. So it's going to be negative 2 plus or minus radical 20 at I outside. So radical 20, you have to simplify it. It's 4 times 5. So 2 radical 5. So it's going to be negative 2 plus or minus 2 radical 5 times I over 4. You break it to identify the alpha beta. So it's going to be negative 2 over 4 plus or minus 2 radical 5 over 4 times I. Simplify it. So that gives me negative half plus or minus radical 5 half of I. This is going to be your R. Okay, any question? Remember, you are going to pick one of them only, one with the positive sign, and you identify alpha and beta. So R equal to the negative half plus, it doesn't matter whichever you pick. But I'm going to call this one alpha and beta. So the alpha is negative half. The beta is a radical 5 half. So write the general solution now. What is the general solution? Y equal to, I remind you, C1 e to the alpha x cosine of the beta x plus C2 e to the alpha x sine of the beta x. Substitute, give us the result. So Y would be C1 e to the negative half of x cosine of beta x radical 5 half of x plus C2, okay, plus C2 e to the negative 1/2 of x sine of radical 5 half of x. So this would be the final answer. Okay, so be prepared for it, in application problems, you cannot have, you may have some terms, especially with the complex numbers, you are ready for it to get these, okay, these numbers. So I'll give you more next time. So what we can do is we can extend it. This is the second order. You can do the cube, the fourth, the fifth, the sixth, but your difficulty sometimes is how we're going to solve those equations. Okay. You may have to use a couple of, have you heard about synthetic method. Solution of a higher order or a higher degree. So I give you a couple of them in the stack. Okay. At least we need to go up to the fourth power for someone to grab. So quickly we extend it. Okay. So far we are done with the homogeneous. Next step is going to be how we're going to find the YC. Remember? Got the YC. So on the next class, I may talk about a little bit about at least one case.